Dear friends, it's great to be back on the Publica stage, but it's also really important for scientists to have this opportunity because we are facing, undoubtedly, in all forms of risk assessment, a very decisive moment for humanity's future on planet Earth. And I'm not talking only about the geopolitical turbulence in the world and the destructive assaults on science and the denialism and populism. I'm talking about risk. I'm talking about the fact that we, for the first time in human history on planet Earth, are forced to seriously consider the risk of destabilizing the stability of the entire planet. What does this mean? Well, it means that we are very close to approaching tipping points where we cause an irreversible drift away from the life support systems that has enabled the world to develop over the past 250,000 years, if you want to take the whole journey of humanity's existence on Earth, or at least the 10,000 years when we've developed civilizations as we know it since we left the last ice age. That's why I picked this picture, the Christmas Day 1968 Apollo 8 Earthrise classic with this steep, transformative, exponential reflection of the moon, because the only currency that matters today to have any chance of a manageable future for humanity is speed and scale. And I'll come to that in terms of the evidence that supports it. So we're talking today of the need to rapidly return into the safe operating space of a stable, resilient, habitable planet. The evidence starts with the Great Acceleration. All the evidence we have of the hockey sticks from 1750 until today, the x-axis is the same time frame. The red graphs here is the socioeconomics. You know the journey. We start burning coal in the late 18th century, and off we go in the industrialized metabolism that leads to GDP growth, resource exploitation, all forms of massive growth, which has had many very important positives in terms of health and better life conditions and the possibility of a world to host now 8 billion people. But look at the right-hand side on the hockey sticks of the impact on the planet. We tend to focus only on the carbon dioxide hockey stick on the upper left-hand corner, but I can tell you, pick any parameter that matters for human well-being, it looks the same. Up until 1950s, we have linear, yes, increased environmental impacts, unsustainable exploitation, but it's the takeoff point in 1955, we're 3.5 billion people, and off we go in the exponential rise in terms of overexploitation of biodiversity, acid rain, deforestation, loss of biodiversity, all forms of pressures on the planet take off at a point where we today conclude in the Earth system sciences that we are in a whole new geological epoch. We're exiting the Holocene and have entered the Anthropocene. Anthros, Greek for humans, we're now the dominating force of change on planet Earth. We're hitting the ceiling of the biophysical processes, the hardwired processes that regulates the very functioning of the Earth system. That is insight number one. Now this is starting to cost us. We have today a situation where we, for the first time last year in 2024, exceeded 1.5 degrees Celsius of global mean surface temperature rise. Dear friends, referencing the IPCC, that's the warmest temperature on Earth over the past 100,000 years. We are already outside of the Holocene range of variability. Now, let me bring you into the lab. Let me bring you into why we are so nervous today, why we have over the past 12 months heard scientific language that I've never experienced in my whole career. Mind-boggling, shocking data, observations that we could never have thought was possible, what would never have been able to predict in our models, and it's this. It is the observations of air temperature on the left-hand side and sea surface temperatures on the right. What you have here is from 1980s on the right-hand side, from 2007 and onwards on the air temperature side. All the gray lines is the annual rise of temperatures, which has led to the scientific conclusion that we have a global climate crisis. This is the graphs you all know. You have on the x-axis temperature and the y-axis burning fossil fuels. It's a linear relationship. The more we burn, the more temperatures rise, and we have entered a crisis because it's starting to cost the global economy and people so much that we are really in a situation of dire need of change. And then comes 2023, and we suddenly jump up in a jump that we've never seen before, a 0.3 degrees Celsius jump in just 1 year, when we normally have 0.03 per year. And just look at the graphs here. The orange line is 2023, the gray line behind it is 2024, showing the same level, but then comes 2025, which is this fat line here, when we would have expected to go back into a, let's say, a normal crisis situation, because we know that the two jumps, 2023, 2024, were El Niño years, which are natural reinforcement years, because it's when the Pacific Ocean releases heat into the atmosphere. But we're now in a La Niña phase. You should expect a cooling back, but we're not cooling back. You may have seen WMO statement report coming out today, which is really worrying, because they predict with an 80% likelihood that we over the next 5 years will breach 1.5 one more time, and that there's a 70% probability that we're stuck at this higher level. This is something wrong. What is happening? The honest answer is we do not know yet. There's a lot of work going on right now to try to explain why are we suddenly in a different trajectory of warming. Why do we see that the hockey stick of temperature in the air to the left and the ocean to the right suddenly shows this decade of accelerated warming? Just look at the graph to the left. This is the climate crisis, 0.18 degrees Celsius per decade of warming caused by us humans. Then suddenly, from 2014 onwards, we jump up to almost 0.3 degrees Celsius per decade of warming. And the 2023-2024 jump, you see it right there. Now, the candidates are discussed very, very actively in the scientific community today. There's a mixture, for sure, of natural variability, the El Niño oscillation, the solar cycle having an all-time, not all-time, but a high level, but also that we have been able to reduce one of the planetary boundaries, namely air pollutants. We have policies, very positive policies on commercial shipping, forbidding sulfate emissions from bunker oil, which reduces air pollutants, which has a huge paradox. We're cleaning up air over the Atlantic, and we're cleaning up cities like Beijing, which of course has a tremendously positive effect on reducing impacts on human health. 6 to 7 million people die prematurely each year because of air pollutants. But the paradox is that that air pollution has actually been cooling the planet. Get rid of it, and we get more solar radiation hitting the surface of the planet. But that cannot explain all of it. Very likely, it's also the hydrological cycle that is ramping up, causing additional cloud dynamics, which in turn has a net warming effect. And the third and final, which is the scariest one, is if we're starting to see a tendency of the living biosphere reducing its capacity to take up carbon. We don't see that statistically yet. The ocean seems to still take up 25% of carbon dioxide from our fossil fuel burning. 25%. It's been doing that for 150 years, leading to ocean acidification, as I'm sure you're aware. But on land, on the other hand, we're starting to see cracks in this carbon uptake capacity. We're starting to see more fires, more bark beetle outbreaks. We're seeing it in Germany, we're seeing it in Norway, we're seeing it in Russia and Canada. We have the latest data of the Brazilian part of the Amazon rainforest, which, did you know this? Planet Earth's richest ecosystem on land, the Amazon basin, has in the Brazilian part, the largest part, tipped over already. It's no longer a carbon sink, it's a carbon source. Now this is a warning sign. And this can be, therefore, the first signs of a planet losing its resilience, losing its buffering capacity, which we in the climate science community call climate sensitivity. You probably heard this holy grail number of 3 degrees Celsius per every doubling of carbon dioxide, which has been guiding our climate science and climate policies for the past 100 years, since Svante Arrhenius in the late 19th century first did the estimates. What if the climate sensitivity is slightly higher? There are many modeling runs showing that that could well be the case. It can be 4 degrees for a doubling, 5 degrees for a doubling, if we have underestimated the loss of resilience in the buffering capacity of the Earth system. And this could be the first signs that that is where we're heading. And if that is the case, dear friends, then of course the global carbon budget gets even smaller, and the pace by which we have to phase out fossil fuels has to go even faster. And this is what we're struggling with right as we speak. That's where we are in the lab. But in 2023, when we touched 1.5 for the first time, we have the evidence now, the costs. We've never seen the frequency and amplitude and strength of droughts, fires, floods, heat waves as in 2023. And the data, you have it here. Just look at the 60% increase of land under drought in 2023. The massive increase of droughts, 50% increase just over that year. We have a massive loss of labor productivity. This is probably the most underestimated factor, that heat is not only a life-threatening impact. In 2022, the latest estimates are that up to 60,000 people across Europe lost their lives prematurely because of heat levels hitting the most vulnerable citizens in Europe. It happened the previous time in 2003, where we also had one of these massive heat events, but this is of course impacting also the economy. So that is where we are in terms of the nervousness. So the question is the nervousness only related to extreme events? Well, it's not. It's also related to what I hinted before, that the planet is now leaving what I call the corridor of life. And the data here is now well established. This is ice core data for the past 400,000 years. You see 3 plates here. Let's focus first on the right-hand side. This is where we are today, at 1.2 to 1.3 degrees Celsius of global mean surface temperature. That could be good to tick off. When we have, in the Paris Agreement, we say we're going to legally hold warming well below 2 degrees Celsius and aim for 1.5. That is the scientific definition of temperature, which is the 10-year moving average. So it's a more persistent breaching of 1.5 that we're talking about. So in 2024, we breached 1.5, but it was a one-year event. But it doesn't mean that we've lost the permanent level of 1.5. We are now at 1.3, actually, in the 10-year moving average. But look at the last 10,000 years, a remarkably stable planet. 14 degrees Celsius, plus minus 0.5 degrees. It's within that narrow range. You have the medieval warm period, you have the Little Ice Age. All variability has occurred within this very narrow range. And then we have the last ice age, 18,000 years ago. We have one more warm period called the Eemian, 110,000 years ago. And then we have an ice age here. And this is 250,000 years ago, when we, as modern humans, start walking this planet, as far as we know today. So we've lived through 2 ice ages and 2 interglacials. Now the Eemian, according to the latest science, as you see, it peaked but never exceeded 2 degrees Celsius. So the broad corridor of life, actually a corridor of life that goes 1 million years back, is that the planet has stayed within a very narrow range, never exceeding 2, warm interglacial, never going below -5, deep ice age. That's the planet as we know it. That's the biogeochemical systems that we depend on. And then we leave the last ice age and we go into an even more stable planet. And we know our journey there. We are just a few million people right here living in caves. We're hunters and gatherers. We have a rough time, massive variability of life support systems until we enter the Holocene, and we barely entered it and go through the Neolithic. This is the domestication of animals and plants. We settle down as sedentary communities and villages. Off we go in the innovation pathways that has taken us to the modern industrial revolution where we are today. That's the journey. And we have so much evidence that it's thanks to the stability in the Holocene that enabled us to take us where we are today. So that is evidence piece number 2. We have a reference point of the desired planet. And that is why it's such a drama to now push ourselves outside of the corridor. The third and final piece of evidence is that the planet is a self-regulating, complex biogeophysical system with interactions and feedbacks. Push these systems too far and you cross thresholds. The system goes from being dominated by dampening feedbacks that cool the planet, that can handle stress like heat imbalance caused by fossil fuel burning, to self-amplifying heat, dominated by positive feedbacks. When ice melts, the surface gets darker. Instead of reflecting 90% heat, a very dampening feedback, it absorbs heat. It becomes a positive amplifier. Now we have mapped the 16 tipping element system that regulates and contribute to control the climate system. 6 of them are up in the Arctic. It's the ground zero on planet Earth, the Greenland ice sheet, the boreal forest system, Arctic winter ice, permafrost systems, connected via the North Atlantic and the AMOC, the Amazon rainforest, 3 big systems in Antarctica. You have the tropical coral reef systems. They are across the entire planet. Large biophysical systems that we're all collectively dependent on because they regulate the stability of the climate system. And here they are. The long list of 16 systems, by the way, they are even in the IPCC, the Intergovernmental Panel on Climate Change. Check up Working Group 1, Table 4.10. 4.10 in the Working Group 1 report. They're there. Well-established science. What is new, which is in a paper we published just 2 years back, is what you see to the right-hand side here. This is the so-called burning embers risk analysis of the likelihood at what temperatures are these tipping elements likely to cross their thresholds. Admittedly, what you see, there's a large uncertainty range for many of them. The darker the color, the higher the likelihood of triggering a tipping point. And you see the temperature range up on the x-axis. I just want you to focus on the top 5, because they have, you see these little white circles there, that's the median level. That is the likely temperature at which they are crossing a threshold where they irreversibly will tip over from a state that helps us and cools us and keeps the life support functioning to a state that drifts us off towards less and less life support and self-amplified warming. And look at the list. The Greenland ice sheet, the West Antarctic ice sheet, abrupt thawing of permafrost, all tropical coral reef systems, livelihoods for over 400 million people, and collapse of the Labrador Sea and collapse of the Barents Sea ice. This is the evidence we have today why 1.5 degrees Celsius is a boundary. It's not a target. It's not a goal. It's something we really need to respect, because go beyond it and we take big risks. Now, we have also more and more evidence that these tipping element systems interact with each other and can lead to cascade impacts. So even if the uncertainty range is large, and even if the temperature levels for triggering, for example, a tipping point in the Amazon rainforest may be higher than 1.5, we have evidence that if the Greenland ice sheet really crosses a tipping point and really starts to flush out cold freshwater in the North Atlantic, that slows down the thermohaline engine that runs the AMOC, the whole overturning of heat in the North Atlantic. Because this is a thermohaline engine that operates from the fact that warm saline water flows naturally from the southern ocean up to the southern tip of Greenland, releases heat, making it habitable in where I come from, up in the Nordic in Sweden. And this heavy saline water, high-density saline water, then sinks and drives the whole AMOC and flows back on the bottom of the ocean back to the Southern Ocean. Now, when that is flushed with cold water and impacted by the ocean dynamics, this whole sinking system slows down and the AMOC slows down. We see a sign of the AMOC having slowed down with up to 15% already today. And we have a cold blob, which is exactly what you expect up in the southern part of the North Atlantic, which is what you would expect because it's the only part of the ocean that is cooling down because of the slowdown of the AMOC. That slowdown very likely pushes the monsoon system further to the south, which can cause less rainfall over the Amazon, which can trigger a higher degree of dieback and explain also why we see less and less rain over the Amazon. But if you get more surface water stuck in the Southern Ocean, this can also explain why the West Antarctic ice sheet is melting faster than we had expected, because you have warmer Southern Ocean than we had expected, because it's not flowing as it should back to the North Atlantic. So this is a reminder that the planet is a very small unit. It's complex, but it's small, it's interconnected, and what happens in one corner can impact many other parts of the planet, and it impacts all of us. So there we are. Here is the evidence sheet. Welcome to the Anthropocene. We're now in the driving seat. We humans are the largest force of change on planet Earth. The Holocene is the reference point. It's our Garden of Eden. And tipping points are hardwired. And this is why we need to quantify the safe operating space for humanity's future on planet Earth. Scientifically, we've been able to do this. We've been working on this for the past 15 years, identifying the 9 Earth system processes that regulate the stability, the resilience, and the life support on Earth. How to keep the planet in a Holocene state depends not only on the climate system, but also on biodiversity, on the configuration of land, on the bloodstream of the planet, the hydrological cycle, nutrient flows of nitrogen and phosphorus, the ocean stability, air pollutants, the stratospheric ozone layer, of course. Novel entities is how much loading of chemicals does the Earth system cope with in terms of nuclear waste, microplastics, PFAS, persistent organic pollutants, before you get permanent changes in genetic composition of species. And all of this has now been quantified with control variables, and this is the latest assessment from, or not the latest, the second most recent assessment from 2023, showing that 6 of the 9 boundaries are outside of the safe space. So this is a verification of why there is even more support for the concern in my first graph showing the acceleration of warming. Because this is exactly what you would expect, that if the climate boundary, because of energy flow, is outside of the safe space, and we are allowing ourselves to undermine the stability of the biosphere, it's not so surprising, is it, that the ocean and the biosphere on land is starting to show signs of weakening the capacity to buffer. Moreover, we are now in a situation where we need to, buckle up for a journey that looks as follows on the screen. This is the 100 or so scenarios from the IPCC that can still hold 1.5 degrees Celsius at the end of this century, but it does have a period of overshoot, and it breaches 1.5 somewhere between 2030 and 2035. We scientifically today consider, when I say we here, it's the Potsdam Institute, I should be clear about that, we consider this is the best that science can, so to say, offer today. Meaning that the possibility of never exceeding 1.5 is no longer possible. We can still hold 1.5, but only after a period of overshoot. And overshoot is, as you see, a long period, 30, 40, 50 years, of up to 1.7 degrees Celsius of warming. This leads to 2 conclusions. Number one is that, I'm afraid to say, with very high degree of certainty, that it will get worse before it potentially gets better. Because every 1/10 of a degree means more extreme events, more fierce extreme events. But the second conclusion is the following. Why would the planet come back after overshoot? And we know the answer. It's that we remove carbon with carbon dioxide removal technologies. I'll come back to that. But also that we come back into the safe space of the planetary boundaries to ensure that we do not cross tipping points, that we keep the buffering capacity of the planet intact. That's why we have now started to release every year an update of the planetary boundary science in the so-called planetary health check. This is the latest version of this. It's the same planetary boundary assessment. Here is a safe space and the safe boundary here. You enter a danger zone in the uncertainty range of science in the yellow space, and here you enter a high-risk zone. We've done it like this as blood sample example to give the communication that we're taking the planet to the doctor to do a full health check. It confirms that 6 of the 9 boundaries are outside of the safe space. The direction of travel, as you see, unfortunately, is still that we're moving in the wrong direction. We've not bent the curves yet. It's starting to cost. This is just headlines from 2024. The global economy is starting to really show signs of double-digit numbers of impact on GDP growth. We published recently, again, the Potsdam Institute, led by Maximilian Koch, et al., a paper with very standard basic climate economics showing that income levels are very likely going to be reduced by 19% by 2050 if we follow the current path as today compared to a business-as-usual development. So we're starting to see big costs to the global economy. And we also know that now, in order to have a chance of coming back after overshoot, we also have to phase out the fossil fuels record fast. And here is the story of the journey. We have 200 billion tons of carbon dioxide in the remaining global carbon budget, 200, to have a 50% chance of holding 1.5 after overshoot. That is equivalent to 5 years of global emissions. It's this journey. We have to phase out fossil fuels at a pace that takes us to net zero by 2050, which is equivalent to 5 to 10% reduction of global emissions per year. That's the pace we have to take. But we also need to transform the global agricultural system from a source to a sink, and we have to start removing carbon dioxide with carbon dioxide removal technologies as you see, at a record scale, up to 5 to 6 to 7 billion tons of carbon dioxide per year. And then we have to secure the carbon sinks on land and in the ocean. So dear friends, this is what science gives us as the best journey. It's a global sustainability transformation. It's a planetary boundary transformation. Even if you care only about solving the climate crisis, this is the journey we have to follow. Now to close, just to say, well, is this possible to achieve? Well, for one, there's no more linear incremental journey that can take us to the right place. It's only S-curves of exponential positive trajectories. And of course, we're looking for these positive, big system changes today, going back all the way to Everett Rogers' 1960s theory of the diffusion of innovation, showing that when you have a good idea, which is better than the incumbent, when you come to roughly 20–25% of adoption, you can have a takeoff point and tip over the logic also in the inert majority that tends to just sit still and not move in the right direction. So are we starting to see double-digit adoption of decarbonized solutions? The answer is yes, and I'm just giving you a few examples here. Here is the renewable energy trajectory. Look at the global south, which is now passing soon 10%. The global north is starting to reach 20% soon. The global south and Africa, South Asia are actually not on linear trajectories anymore. This is often forgotten, that even the global south is really moving on a non-linear exponential pathway on renewable energy. This is the classic story that we have all started to learn about, the Norwegian social tipping point on electric vehicles. Just look at this S-curve. 90% of vehicles sold in Norway today are full electric. I take that again, 90%. They would never return to the internal combustion engine. But remember that Denmark is also on that path. Just look at Denmark, almost at 60% penetration of electric vehicles. Often I get told, well, but you know, electric vehicles, that's an easy thing. But I've just been playing around. I say playing around because this is unpublished, so let it stay in this room. Here are just a list of the difficult-to-abate sectors. I mean, we're talking steel, cement, fertilizer, plastics, chemicals, transport, food system. These are generally considered being really difficult to have any solutions for. But when you just map and talk to the industrial leaders in the world, there are solutions. And they've come quite a long way. I assess it like this, that you have in green areas that are starting to now be possible to commercialize, possible to really start scaling. And we're talking steel, fertilizer, food system transitions, and of course, mobility. It's a race going on right now. Admittedly, you have a few difficult ones like aviation and plastics, but it's not as if this is an impossible problem to solve. So therefore, I leave you with this. We have accumulated for the first time all the planetary boundaries into one assessment. We placed the planet in our expert elicitation and all our analytics where you see the planet there. What does this tell us? It tells us, number one, we are in danger. Admittedly, we are outside of the safe space for the health of the entire planet. But secondly, it also tells us we're not yet in the red zone. We're not yet in a place where we do not have an opportunity to transition this around. And I was very inspired when Billie Eilish was in Berlin just a few weeks back, and her dramatic song, When the Party is Over, making clear that the fossil fuel era is now at the beginning of the end. And I agree with that. But the scientific message is also that the game is not over. The window is still open, even though it's gradually closing or quite rapidly closing. But we have a chance to turn this around, and we have the solutions. And in the other end, we know we'll come out stronger, healthier, more secure, and more competitive in a more modern future than before. So therefore, it's so important to stand up with science today in a world that is suddenly in a very shake-up on this agenda. Thanks for your patience.